Hello. We are going to solve a heat engine problem. It almost looks like there is information overload, but as you dissect the problem, you'll see it's quite a simple problem really. So what are given? The two reservoir temperatures, the hot and cold temperatures are given to us, and the net power is given. Also is given the heat transfer from the hot reservoir to the engine, that is Q dot H is given. And let's determine the thermal efficiency of the engine. So in symbol, what is given is Q dot W dot net is 200 kilowatt, and Q dot H is given to us to be 400 kilowatt. And notice that TC and TH are also given. One could just jump into Carnot efficiency thinking that that's what is wanted. No, it says find the thermal efficiency of the engine. And by definition, the thermal efficiency, if you recall, is the desired output and the required input, which is Q dot H. So it simply becomes 0.5 or 50%. So the temperatures are not being used in this problem, at least for the part A problem. The second part B, is the rate of fuel consumption to maintain the hot reservoir at steady state. So see, the hot reservoir is supplying heat at the rate of 400 kilowatt to the engine. So how much fuel has to be burnt? So to solve this part B, notice that the heating value, which is given as 45 million joule per kg, can be written as 4500 kilojoule per kg. So if then fuel consumption is m dot f, so much fuel is consumed every second, and if you multiply that by the heating value, so the notice what is the unit, just kg per second of fuel consumption and kilojoule per kg of heat release. That gives us kilojoule per second or kilowatt. So m dot times hv must be equal Q dot h, which is 400 kilowatt. So it's a really simple problem. All we are doing now is finding what is fuel consumption rate, because the heating value is given 4500. So it becomes a very simple problem. So therefore, m dot f, the fuel consumption rate in kg per second, is 400 kilowatt divided by 4500. So many equals 4 divided by 45 kg per second. And that translates to, if I multiply by 3600, it becomes 320 kg per hour. The second part of the question is, suppose the engine, the minimum possible fuel consumption rate for the same output. So the net work would be still 200 kilowatt. The engine will be still producing 200 kilowatt, and we want to find what is the minimum fuel consumption. Obviously, if the fuel consumption has to be reduced, that means if you look at the formula, fuel consumption times heating value equals Q dot H. So Q dot H has to be minimized to minimize the fuel consumption, because the heating value, which is if you burn 1 kg of fuel, how much of heat is released, is a property of the fuel, not property of the engine. So for a given fuel, heating value is a constant, 4500. So therefore, to minimize m dot f, we want to minimize Q dot H. If you look at the formula for thermal efficiency, to minimize Q dot H for the same W dot net, the efficiency must be maximized. And we know the maximum limit of the thermal efficiency, which is the Carnot efficiency. So using the Carnot formula, eta thermal Carnot equals 1 minus Tc divided by Th. And if we substitute the values of Tc and Th that are given to us, we'll get this to be 0.85 or 85%. So that produces immediately q dot h, minimum possible q dot h, becomes w dot net by thermal Carnot, which is 200 by 0.85 to 35.3 kilowatt. And therefore, the fuel consumption rate now can be found, which is 235.3 divided by 4500. So many kg per second times 3600. I believe that will turn out to be 188.2 kg per hour. Well, the problem is solved. Let's see if we can get the Carnot efficiency, the thermal efficiency of the engine by using a test calc. I've already logged in. Go to test calc. Again, heat engine is a closed system which runs at steady state. So we click here. And to launch the test calc, we go to the tab and we hit the run button. And this Lego, sometimes Java is not allowed, then you have to go and say allow Java here. Okay, so notice that there are three different radio buttons here. Heat engine is already chosen. If it's a refrigeration problem or a heat pump problem, we select the appropriate radio button. Okay, so what is given in this problem? First, what are given are, we know Tc is 300 Kelvin. And Th is given. What is Th? 2000 Kelvin. So of course, just from this temperature, we can calculate thermal efficiency, Carnot efficiency, 1 minus Tc over Th, very simple. But what is also given is q dot h and w dot net. So let's enter those. W dot net is 200 kilowatt and q dot h is given as 400. It's of course a very simple problem, but so you can still see that to understand this test calc, w dot net by q dot h will give you the thermal efficiency, which is 50%, and the Carnot efficiency is 86.8%. So that's what we got when we solved it manually. Oh, sorry, we got 85% for some reason. So I think I made probably a slight mistake. So that's why we verify solution. 1 minus 300 over 2000 should not be 85%. It should be close to 86.8%, so 87%. Okay. So please check my manual calculation. I must have made a mistake. So now that we know Carnot efficiency and the actual efficiency, finding the mass consumption rate, you can calculate using a calculator, or you can do it here. This doubles up as a calculator. For instance, we can write down equals, for instance, to find out fuel consumption rate. We know it's 450. 400 is the heat transfer q dot h divided by 4500. So that is the mass consumption rate, fuel consumption rate in kg per second. And if you multiply that by 3600 times 0.0888, so it's about 320 kg per hour. So that's what we got for the first part. So I guess it's such a simple problem, there is no point carrying on. So you can see that even here there's a possibility of a mistake. The eta Carnot that we found here, 1 minus Tc over Th, it should be 1 minus 300 divided by 2000 should have been 85, 0.85. And oh, I see. Sorry, we made a mistake here. It's 2000 Kelvin. 2000, I put Celsius. Kelvin, calculate. Okay, so we didn't make a mistake in our manual solution. We made a mistake here because we picked Celsius instead of Kelvin for the TH. And notice that in the I/O panel, we did get the correct answer because when I use the temperatures here, I use 2000 Kelvin, so obviously I use the correct formula. Whereas here, I picked the wrong unit. That's what resulted in a wrong solution. All right, I'll stop here. And there are plenty of problems in chapter 2. Solve a few more to make sure you master how to solve heat engine problems.